It's my great pleasure to welcome here Professor Babai from the University of Chicago, and he will talk about irregularity, Johnson graphs, and you know what. Let's see.
Okay, thank you. Well, that's the title. Hidden irregularity versus hidden structure. And the Johnson graphs are going to be the representatives of the hidden structure. So it's not arithmetic progressions or some other regular configurations that you are used to. Well, okay. So, this is a regular graph. But if you were asked to expose some irregularity in it, you would have no difficulty. So for instance, those 4 vertices do not belong to any triangles, and all the others do. All right, so that's something that I managed to split up the set of vertices in a canonical way. It is a good coloring, no dominant color, no color appears 90% of the time. If you go back and see, another thing that would make me happy is if I found a good equipartition, partition into equal parts, that's canonical. And canonicity means that it is preserved under isomorphism. So if I take 2 copies of this graph and I take an isomorphism between them, then the green vertices are going to be mapped to green vertices, and the pink vertices are going to be mapped to pink. So in that sense, the structure that I superimposed on the graph is canonical. Now, I mentioned equipartitioning, partitioning into equal parts. Why would I not consider partitions into unequal parts? Well, I can, but if I do that, suppose here is a partition that is somehow canonical with respect to a structure that I didn't show you, then I can immediately color it by colors by simply every vertex gets a color that is the size of the block to which it belongs. And so I am back to coloring. But what I find is that vertices that have the same color, they are actually equipartitioned. They are partitioned into equal parts. So I don't need to worry about partitioning into unequal parts. Okay, so canonicity means if I have an input structure and I associate some other structure with it, for instance, x is a graph and f of x is a coloring of the vertices, then canonicity means that it not only assigns object to object, it also assigns isomorphism to isomorphism. So if I have 2 input objects, like 2 graphs, and I have an isomorphism between them, and I look at the corresponding colorings, then there is a corresponding isomorphism between them. So this is what is called a functor, because it also satisfies this equation, and this happens to be a functor now from the category of isomorphisms of graphs to the category of isomorphisms of colored sets. But colored sets could be any other object that I superimpose on my graph, and canonicity has the same definition. Okay, all right. This looks like the most regular object you have ever seen. Every vertex looks alike. It's very harmonious. But if I individualize one vertex, then immediately it turns out I can already split up the entire thing into pairs. Only 2 vertices are going to have the same distance from this point that I individualized by giving it an individual color. And if that's too much for me, then I individualize a second one, and now every vertex is different. So by individualizing these 2 vertices, I destroyed every regularity. Every vertex now has its own individual label, which I could denote by color, but I didn't have enough colors. That's 22 vertices. So, okay, let's look at a more resilient example, that is where the symmetry is not so easily destroyed. Petersen graph. Okay, so if I individualize a vertex, then the neighbors are immediately going to notice that, oh, I have a little red star in my as a neighbor, but the others are not going to do anything. So if I want to get any further, I have to individualize a second one. So still before that, we see that more than half of the vertices still are glued together. They belong to a block. Now, after I do this, then I propagate this disturbance that I just introduced, and I end up again with a coloring where every color class has at most 2 vertices. So this is clearly a graph that doesn't like to be destroyed so easily. with two vertices, I still have these pairs together, and I would need to individualize one more to get complete split. Okay, so, but in any case, I made substantial progress in chopping up the graph by individualizing two vertices. The problem is individualization is not canonical. If I have two graphs that are isomorphic and I individualize the vertex in the other one, I won't know which vertex in the other one that should correspond to, so I should individualize every possible vertex on the other one. So this has a multiplicative cost. What I get is not a canonical example, but a canonical set of examples. In this case, it would be 10. So 10 copies of the graph, each of them individualized at a different vertex. That's what I get. That's canonical. So I call this a multiplicative cost. So if I want to do algorithms for like graph isomorphism testing, then it multiplies the running time by a factor of 10. So it's a branching factor. Yes?
Nice. So could you repeat the definition of canonical?
Oh, canonical, okay. So an object that I have a class of objects like graphs, and I assign to each of them some other object like a coloring of its vertices, okay? This is canonical if I not only assign colorings to graphs, but I also assign isomorphisms of colorings to isomorphisms of graphs, okay? So if it is a functor, okay, that's what I mean by canonical. Yeah.
Okay, so now you're saying that this thing is not canonical? Once you label the vertex?
Well, I label the vertex, that's not canonical, because it is no longer true. Suppose I have this labeled vertex and I have this. Okay, it is no longer true that every isomorphism between the original graphs induces an isomorphism of my graphs with
That's the reverse of what you just said. That's why I'm a little confused about the definition of canonical.
No, every isomorphism of the graph should induce an isomorphism of the objects to which I assign to it. Of course, not conversely. I mean, colored sets will have a lot more isomorphisms than the graphs which I colored. So they don't have to have that structure that the original one has.
I don't know if you want to go into this, but if you replaced every isomorphism by there exists an isomorphism, this is still canonical. Right?
This is the only reason this is canonical, because this is a vertex transitive graph and we don't even have an efficient test of that fact. And in general, what I'm trying to do is imagine here a highly regular graph of which I do not know whether it has automorphisms. And I can't draw some small examples of that, but you know, this basically the smallest example would be 16 vertices, where I could begin have such an example. Okay, all right. So anyway, so this is the general concept of the multiplicative cost. Okay, so if I, for individualizing a vertex, if I have any structures x and y, it could be hypergraphs, it could be relational structures of hierarchy, whatever, then this is my notation for the set of isomorphisms. And now I subscript this by x. X is the vertex that is being individualized. It doesn't have to be a vertex. It has to be, so for instance, I can individualize a triangle, or I can individualize any associated structure. Okay, so if I look at all isomorphisms between x and y, and I individualize a vertex little x in this fracture x, then I have to try the same thing for every possible way of individualizing the same type of object in y, and that's how I get all the isomorphisms. So this gives me a branching factor. If it was individualizing a vertex, it was then a factor of n. If I individualize t vertices, then the multiplicative cost is going to be essentially n to the t. Okay. So now here is a question then. Given a non-trivial regular graph, by non-trivial I just mean it's not complete and not empty, can we find a canonical good coloring? Good coloring means no color appears more than 90% of the time, so there is no overly dominant color. Or equipartition, by that I mean that I already have colorings. There is a dominant color, but the dominant color is split up into equal parts at a modest multiplicative cost. So that's the question. And the answer is no, the Johnson graphs are resilient to good coloring or partition. So here is the definition of Johnson graphs. I take two parameters, k is at least 2t plus 1. I take a set of k elements, that's v, but I'm sorry, that's delta. Delta is a set of k elements, and I look at all t subsets of that. So there are k choose t of those. So that's going to be the set of vertices. So the set of vertices is associated with the set of t tuples of a set of k elements. And two of these vertices, one of them labeled by a subset T, the other labeled by a subset S, these are T element subsets. They will be adjacent if they differ minimally. Okay, so their difference is just 1. And one can show that the multiplicative cost of good coloring or equipartition of the Johnson graphs is exponential in k over t. Now, the case t equal 2 is a very important one. In this case, n is k choose 2, so that's essentially k squared, so the cost is going to be exponential in square root of n. And this square root of n has been one of the, not the only one, but one of the exponential of square root of n bottlenecks for 3 decades for graph isomorphism. So, so we have to deal with this in some way. Okay, the good news is that Johnson graphs are the only obstruction to good partitioning. So here is the split or Johnson theorem. Given a non-trivial regular graph, then at quasi-polynomial multiplicative cost, one can find one of the following things. Either a good canonical vertex coloring, okay, so no color appears 90% of the time, or a good canonical equipartition, so there is a large color, but it is chopped up into equal parts, or a canonically embedded Johnson graph on a dominant vertex color class, so a large Johnson graph that's hiding under the surface there. So quasi-polynomial means exponential in polylog, and canonicity, as I said, means a functor. So that isomorphism, for instance, if what I find is a hidden Johnson graph there, then any isomorphism of my graphs must also induce an isomorphism of the Johnson graphs hiding underneath.
What do you mean by embedded?
It's just that the same set of, so as the set of vertices is going to be one of the color classes. And the relation, I don't say anything else about the relation, so the adjacency relation in that Johnson graph, other than that it is canonical. Okay? So, for instance, if it is definable by some formula from my original structure, that would definitely be canonical. But I don't insist on that either.
Embedded means an induced subgroup.
No. It means nothing other than it is behind the scenes there and canonical. So it is, imagine that I have a graph and then I define another graph in it, which is not a subgraph. I define it to be distance 3, the distance 3 graph, okay? That's not a subgraph, but it is clearly a canonically embedded object there, okay? So the word embedding is only for the vertices being a subset, and then, of course, by definition, the vertices then have to be a canonical subset, so it has to be, I can use it as a color. Yes?
If we're given a good partition of, say, 2 graphs, to check if they're isomorphic then, do you just check equality since they're canonical? Like, say, there's no Johnson graph if you just give it 2 good.
No. This is, okay, so regarding the graph isomorphism problem, this would be a step in a divide and conquer recurrence. So just the fact that I have 2 big graphs and I chopped off 15% from one of them and also from the other, so I know that this 15% corresponds to that 15%, we can't get very far from that. So there is a lot of work then, but this simply ties into a recurrence that is group theoretic, and I'm not going to give the group theoretic details today. Yes?
So I'm still trying to understand what you mean by embedded. So does it mean like topologically embedded, or is it?
No, nothing. No, none at all. None at all. Logically embedded, maybe I could say. So the vertices are a subset, and the adjacency relation can somehow be defined from my structure.
Okay.
Okay?
So it would be a case.
So two of them. So for instance, just let me give you an example of the definition. I have a graph, and now I make two of the vertices adjacent in a new sense if the number of triangles attached to one of them and attached to the other, there are, I don't know, there are 25 pairs of such triangles that share exactly one vertex. Okay?
So
Yes.
can you say this is some sort of functorial subset of vertices?
Well, so the exact definition is that this assignment is a functor. That's it.
And it's a subset.
Preserving isomorphism.
It's at, yes, so it is on the subset of, so it is a structure on, it is a graph in this case, or structure on the subset of vertices, and this assignment is a functor. A functor in the category of isomorphisms.
Interpretation. You said logically it might be called interpretation. You interpret your new adjacency relation with integration.
Right, the new adjacency should be interpretable in the old, yes, that's true.
Now it's no longer.
But it doesn't have to be efficiently interpretable, so it could be that it is an exponentially large formula.
It's just definable. Is it clear that having an embedded Johnson graph means that you won't be able to find an equipartition, a canonical?
No, it doesn't. No, that's a question to which I don't know the answer. That's a very good question, and I would like to know the answer to that. Basically, I would like to see this result strengthened in such a way that that situation is moved to part A or B, and part C only occurs when the symmetries of the Johnson graph actually are manifest. But okay, so that I don't know.
So it's possible that A, B, and C are all possible for some graph.
Oh yes. Oh yes. Yes. No. That. No. I'm sorry. That all. Oh sure. No. If my. Okay. If my. Of course they are possible. If I take a random graph, then one can canonically assign an ordering to the vertices, and then you can define every object from that. Okay. So if every vertex already is differently colored, then you can, just using those different colors, you can define any object that you can associate with it. So that certainly, and then of course you can have colorings, you can have partitions, and you can have your favorite graphs embedded right there. Okay. Yes?
Can you say which logical language you're doing the interpretation? Like you've been saying things about counting adjacencies, so you need like counting quantifiers at least, right? So
now we are talking about finite sets. Okay, so if I allow first order formulas in ZFC, not in the language of just one relation, but in ZFC, then I can do anything.
But the question is about uniformity. I guess that you have a single formula that works for all graph sizes. So
no, that I don't insist on that. No, it doesn't have to be.
And it does not come from your proof.
I'm not looking at formulas. I am only looking at the notion of a functor. Okay. So all these examples, when I define it by a formula or define it in some explicit way, these are just special cases by way of example. But the definition is that that the assignment has to be a functor. Okay. So this is the only thing. Okay. Here is a graph, and I assign some structure to it. Here is another one, I assign structure, and here is an isomorphism between those two graphs. Then they should induce an isomorphism of the assigned structures. That's it.
Fine, that's it. I think the way I interpreted that question is it conceivable that you can actually restrict the kind of the embedding? Make it logically simple in some sense.
I'll think about that. That's a question I never tried to simplify that. But in one sense, I can tell you that it is not an arbitrarily complex thing. I can construct it in quasi-polynomial time, right? So that is already a notion of being not too complicated. Yeah. But it would be interesting to look at what kind of formulas. I mean, formulas that are clearly dependent on the graph. There are formulas, but I doubt that there would be a formula that's independent of the graph. Well, in ZFC, everything is possible. Yeah. Okay. All right. So that's the theorem. And and now, okay, so let me get it into just a slightly more general context, but it will be the right context. So if I have a structure, then I say that two elements of the underlying set are twins if the transposition of those two objects is an automorphism. So if those two elements are interchangeable while fixing everything else. So it's pretty obvious that the twin or equal relation is an equivalence relation. And now I define the symmetry defect. So the symmetry defect is that I take the complement of a largest set of largest twin equivalence class. So twins form equivalence classes. I take the largest one and the relative size of the complement. That's what I call the symmetry defect of the structure. Okay? So if the symmetry defect is small, that means that a huge symmetric group is acting on my structure while fixing everything else. Okay, so these are sort of bad cases for my attempt at splitting things up. So for instance, if the automorphism group of this structure is the entire symmetric group, then of course there is no attempt at chopping it up could possibly work. So those need to be excluded. And also when the symmetry defect is very small, that is not going to then permit. So if I put this threshold at 90%, of course this 90% was an arbitrary number. Any number greater than a half would do. But I like 90% because that already shows that something big is happening. So if I have a symmetric group acting on a subset that's bigger than 90%, then I cannot chop off 90% canonically. Okay. So for instance, here is an example. If the automorphism group is, so imagine that our structure has two colors. That's all. That's the structure. K elements and n minus k elements. Then the automorphism group is the direct product of a symmetric group of degree k times the symmetric group of degree n minus k. And the symmetry defect then by definition is k by n. So I look at the small, if k is less than n over 2. So I take the smallest of these two numbers and I just take the proportion of that. So that's the definition of symmetry defect. Okay, I'd like you to remember this definition because this is the central, one of the central. In fact, for this talk, this is the central definition. Okay, so once again, small symmetry defect means very much symmetry, and large defect means that there could be still a lot of symmetry, but they don't cluster together. They don't form a symmetric group acting on a large set. Okay. So a little exercise, if I have a non-trivial regular graph, then the symmetry defect is at least 1/2. So there cannot be a symmetric group acting more than half on this. Exactly half could. I could take the complete bipartite graph with equal parts, then a complete symmetric group reacts on one part and also on the other part. That has symmetry defect exactly 1/2. But it cannot be, the defect cannot be less than that. Okay? And now here is the full version of the Split-Johnson theorem. So I get rid of the assumption that my input graph is regular. And instead, the condition is that it has symmetry defect bounded away from 0. Okay? So say at least 10%. Then at quasi-polynomial multiplicative cost, we can find one of the three options. Okay, that's the. Why is this the real thing? Because the symmetry defect condition is not only sufficient; it's obviously necessary. If I have a bigger symmetry defect, then I cannot do any of the three things here. It's also important that the proof is recursive, and this is the invariant that we preserve. Okay, when we go to smaller instances, what we preserve is the symmetry defect.
So is that less than defect less than or equal to? Or
no, the defect has to be at least something. So a defect is the complement of the symmetry. So I don't allow more than 90% to be glued together and being completely interchangeable. Okay? All right. So yeah, so that's why I call it symmetry defect. How much is missing from that symmetry? Okay, all right. Now, another thing is that we extend this result not just to graphs. So my input is not going to be a graph, but it is going to be a relational structure. A K-array relation is just a subset of the Cartesian power of my underlying set. A K-array relational structure is a set together with a list of K-array relations. And then the design lemma, what I call the design lemma, is again about K-array relational structures with symmetry defect at least 10%. The claim is, and somehow there is a typo here, one can individualize k minus 1 vertices. Individualizing negative 1 vertices would really not suffice. Does anybody know where I can find markers?
That's a board.
What's a board?
Oh, I see. Yeah, okay. Okay, so we are individualizing k minus 1 vertices. Okay. Okay, so there is a set of at most k minus 1 vertices which we can individualize, and we can do all this in n to the big O of k time, and we find one of the three options: good canonical coloring, good canonical equipartition, or a canonically embedded regular graph. Now I don't have to say more, because regular graphs then can be pushed all the way to Johnson. So that's a separate, and the reason there are several reasons why I am separating it, but I could say it in one, simply replacing the third option by the Johnson graph. Okay, because if I have a canonical regular graph there, and from that I construct something that's canonical with respect to the regular graph, obviously this is a transitive relation. So, so we can then push all K-array structures with symmetry defect at least 10%, we can push it all the way to the Johnson graphs. Or we have A or B. Okay, so that's but part of the reason this is separate is that the method of proof is entirely different. Also, there is a parameter k here. And so I'm not claiming here that this can be done in quasi-polynomial time. It depends on k. And in the application to graph isomorphism, k will be of the order of log n, in which case this is quasi-polynomial indeed. Yes?
So I want to make sure I understand. So this last condition, so you're starting with a k-array relation.
Right.
But then in part C, you embed a binary relation.
That's the point, yes. So I am reducing, so this is the k to 2. This is the reduction where I am reducing k-array to binary. And then with the binary, the design lemma, the split or Johnson continues from there. Okay, so this algorithm basically produces an input to split or Johnson. Either finishes the job already in A or B, or produces an input to split or Johnson, and then from there we go on to either still get A or B, or get the Johnson graph. Okay, all right.
Should we see why k equal log n is graph isomorphism, or is that just a remark? Should we understand why that's the case?
Give me a minute. I will not make you understand it. I will answer the question whether we should. Yes. Okay, so what is the significance of this result to graph isomorphism? Graph isomorphism can be reduced by way of group theory to the following problem, encasement problem, okay? So the encasement problem is that I am given a graph, or more generally a relational structure with symmetry defect at least 0.1, and I want to find okay, so in that case, I know that its automorphism group doesn't have order n factorial. It is not the symmetric group. In fact, I know that the index of the automorphism group in the symmetric group is exponential. And now I want some explicit demonstration of that fact. While I am not able to determine the automorphism group, I nevertheless would want to be able to get something intermediate. So I want to have a subgroup that includes the automorphism group and has exponential index in the symmetric group. So this is a key recursive step. The recursion goes on somehow on some group that is somewhere there, and that group I want to reduce, and in the bottleneck case is really it is the symmetric group that I have to reduce. So this is what I'd like. And I am not able to solve the problem as I just stated in verbs. What I am able to do is, however, find a small subset that if I individualize that, then I can encase that. Now this individualization, if I only individualize the logarithmic number of points, then that only creates an index of n to the log n. So this is still much bigger than that. So I want to really push things down. I can't push down the automorphism group, but something that is very close to that. It's only n to the log n away from it. That I am able to push down, and that is sufficient for the divide and conquer application to graph isomorphism. And this problem, this encasement problem, so I want to encase the automorphism group or something close to it in a known subgroup of large index in the symmetry group. This problem is solved by combining the design-lemma and Splitter-Johnson, solved in quasi-polynomial time. Okay, so the reason I had to limit k to order of log n and the size of this set to polylog n, okay, to get it down in quasi-polynomial time. Okay, now you see that there is an asterisk right here. So graph isomorphism can be reduced by way of group theory to this problem, and this problem is solved by Splitter-Johnson. That's here the explanation of the footnote, and I think that answers the question. Okay, so I'm not talking about the long thing, which is the heart of the graph isomorphism problem. I took as my cue somehow the title of this workshop, and that is seems somewhat related to the Splitter-Johnson, so that's what I'm talking about today. And that's why I had to, in spite of the fact that about this graph isomorphism result I already gave more than 24 talks, I had to write 70% new transparencies. So all of these are very recent, most of them. Okay. All right. So let's see, why does design-lemma and Splitter-Johnson solve this encasement problem? Okay. If we found a good coloring, then that's clear. The index of sk times Sn minus k in Sn is n choose k, which is greater than n over k to the k. Now in this case, k is at least 10%. So n over k is at most 10. What am I saying? Oh, but it's at least 2. I should have written 2 here. Okay, but the exponent is going to be n over 10. Okay, no, I should have written 2 here and then 2 to the n over 10. That's definitely, no, this 10 is a mistake here. In the exponent n over 10 is fine. So it's exponential. It's exponential in n. If I have a good partition, then that will be even better. It will be close to 2 to the n. But what if I get the Johnson instead? Okay, so if I get a good coloring or a good partition, then clearly I managed to reduce the group substantially. But what if Johnson is found? Well, the automorphism group of the Johnson graph, JKT, is just the symmetric group of degree k. Remember what this is. This is the set of vertices is t subsets of a k set. And one can show, not difficult, that every automorphism of this graph is actually induced from just that small set of size k. So it has k factorial elements. K factorial is essentially exponential. It's essentially n to the it's exponentially n to the 1 over t. Okay, so this is t is at least 2. So this is exponential, at most exponential in square root of n. Now, that means that the index is virtually n factorial. This is a dramatic reduction. Okay, this kind of reduction, exponential reduction, you can do, if you repeat it, you can do it log n times. Okay, n factorial is essentially n to the n, which is exponentially in n log n. So if you chip off an exponential in n, you can repeat it log n times. But taking square root, you can only do log n times. If you could repeat this, so this is a much more dramatic reduction of the group. And so what this means is that really the Johnson graph is annoying because it didn't allow us to do a partitioning. But once we found that Johnson graph, then we managed to make enormous progress. So Johnson graph then turns into our best friend. Okay, so what type of target recurrence do I have in mind that will somehow result in a quasi-polynomial bound? So we are talking about the divide and conquer algorithm, which means if we reduce a problem instance to a moderate number of significantly smaller instances. And so for today's talk, a moderate number will be a quasi-polynomial number, and a significantly smaller instance will be bounded away from 1. So it is at most, say, 90%. And then the target recurrence looks like this. If f of n is the cost of producing whatever I want to on instances of size n, then here is this multiplicative cost factor, q of n, times, and then what I plug in here is just 90% of that. Now, if this multiplicative cost is, okay, so if I solve this, I iterate this, I can only iterate it log n times, so the solution is going to be this branching factor raised to the power log n. So if the branching factor was quasi-polynomial, then this is still quasi-polynomial. So that's what we want then. We want, so this moderate cost, we want it to be quasi-polynomial. Okay. Now, let me quickly talk about the naive refinement method that I indicated at the beginning in pictures. So the input is a vertex colored graph, and the output will be a refined coloring. What we do is, if C of x is the color of a vertex, and di of x is the number of neighbors of x in color I, then in the refinement step, simultaneously every vertex will learn that information. Every vertex will learn how many red neighbors it has, how many green neighbors it has, and etc. And that will be encoded in the new color. Okay? And we keep doing this until no refinement is obtained, until it stabilizes. Now, the stable colorings are very easy to characterize for this. And if I have a graph and I partition the vertices, this partition is called equitable if each color class induces a regular subgraph and each pair of color classes induces a semi-regular bipartite graph. Okay, so this is if and only if. So these are the stable configurations for this naive refinement procedure. Okay. So, for instance, if the graph is regular, then this procedure doesn't even start. It doesn't do anything. We get no. But in general, the first round gets us classifies the vertices by degree. That's the first round. And then, of course, we can move on. But for regular graphs, we don't even start. Okay. Now, the opposite end of the spectrum, so regular graphs, it keeps it all together, doesn't do anything. The opposite end of the spectrum is that if we keep doing this, then eventually we completely split the graph. Every vertex gets a different color, and the colors form an ordered set. So this is a canonical labeling then of the graphs, and it is a canonical labeling in an extremely strong sense. If I did that to my graph, and here is another graph, of course, if the same thing doesn't happen to the other graph, then they are not isomorphic. If the same thing does happen, then there is only one candidate isomorphism left. So, and this is what we proved with Erdős and Selkov long ago, that for almost all graphs, actually complete split occurs in 2 rounds. So isomorphism test for almost all graphs can be done in linear time. And now I'd like to state an exercise, which is one of the favorite of mine, even though it's not going to be related to anything else that I'm saying. If the characteristic polynomial of the adjacency matrix of the graph is irreducible, then naive refinement leads to complete split. Okay? So what you have to prove is that in this case, there is only the discrete partition is equitable. Okay. All right, so a more advanced refinement method was invented by Wersteller-Leman in 1968. This is a time which was contemporaneous of the notion of polynomial time. So that's when the notion of polynomial time gained popularity. And so they decided to classify not vertices, but pairs of vertices. So it is basically coloring the edges of the complete directed graph. So here is the information. Suppose I have a pair of vertices, and I look at a pair of colors, red and green, and I count the number of two-step walks. First step is red, second step is green, from the tail to the head of an arrow. Now, this is the information that I'm going to include in the next round in the color of my pair. So maybe now my pair is green, is blue, but in the next round it is going to be refined. It is going to be navy or light blue or something, depending on how many red-green two-step walks it has from its tail to its head. Okay? And a coherent configuration is a coloring which is stable under this refinement. Okay? Okay. So if my input is a graph, I can think of it as a rank 3 configuration. So there are 3 colors. One color is going to be the diagonal, the pairs of the form XX. And then there are the edges, and there are the non-edges. So there are the edges of the complement. Okay? So we start off with 3 colors. And now we try to refine. Some graphs resist. They immediately refuse to be refined. These are precisely the strongly regular graphs. They are the ones that are already at this stage stable under Wersteller-Leman refinement. Okay, so a coherent configuration of rank R is a partition of V cross V in R parts. And these parts I am referring to as constituents. These are digraphs. These are directed graphs. So coherent configuration is so a stable configuration under Wersteller-Leman refinement. And I am going to say that if the color of a pair is I, if the pair itself belongs to the I's constituent. Now, here are some axioms that define coherent configurations. First of all, we assume that diagonal colors and off-diagonal colors are never the same. Another assumption is that the color of a pair determines the color of the reverse pair. And the third thing, now this is the interesting condition, and this resembles the definition of strongly regular graphs, if you know that, that for any pair of a certain color, if I count the paths of length 2 in another pair of colors, then that only depends on the color of the pair that we started from. Okay, so this is just expressing that this is stable under Wersteller-Leman refinement, and these parameters are called intersection numbers. So the intersection numbers depend on 3 colors, I, J, and K are colors, and what they mean is that I take the first color and I look at the paths of length, walks of length 2 in the other 2 colors from the tail to the head. Okay, that's that counting. Okay, all right. So here is an example of a coherent configuration of rank 7. For some of the arrows, for some of the edges, I put an arrow there, and the meaning of that is that the reverse arrow has a different color. So there would be a purple, and there would be an inverse purple. I just didn't want to make a mess out of the picture. On the other hand, if there is no arrow, that means that it is a self-paired relation. It means that if you swap the variables, it still remains. So it's a symmetric relation. Okay, so altogether, these are the colors there. There are the diagonal colors, red and blue. They are undirected off-diagonal color is orange. And then there are the off-diagonal directed colors, which are purple, its inverse, green, and its inverse. Okay? This is actually something that arises from a group. So if you think of the symmetric group permuting the left 3 vertices and the cyclic group permuting the right 3 vertices, okay? Look at this permutation group and look at its orbital configuration. The orbitals are the orbits on pairs. So this group induces an action on the pairs, and 2 pairs are in the same orbital if there is an element of this group that moves this pair to that pair. Now, if we color all pairs according to these orbitals, that's we call the orbital configuration, and that's the context in which Schur introduced this entire combinatorial setup in 1933. Okay, so this is at the moment only a heuristic statement, but I believe this should be actually made precise, that most coherent configurations don't come from the group case. So in particular, those that come from the group case have these as their symmetries, and I believe most don't have any non-trivial symmetries. Okay, some more concepts about coherent configurations. A configuration is homogeneous if all vertices have the same color, and it is primitive if it is homogeneous and every off-diagonal constituent is strongly connected. Now, I am putting strongly in parentheses, and that's an exercise that if I have a homogeneous configuration, so every vertex has the same color, then the weakly connected components are strongly connected. Okay? So this is an imprimitive configuration. This is primitive. Why is this imprimitive? If I look at the green color, that's connected. However, if I look at the blue, then that's disconnected. And if I look at the red, that's again disconnected. Okay? On the other hand, if I look at the pentagon configuration, then there are only two off-diagonal colors, and both of them are connected. So this is primitive, and this is imprimitive. And so that's an important structural distinction, and in a way, in a sense, in a vague sense, one could say that all coherent configurations are built up from primitive ones. This is really not really true, but nevertheless, one can say that if we learned a lot about the primitive coherent configurations, then we learned a lot about general coherent configurations also. An example of primitive coherent configurations is the Johnson scheme, which has k choose t vertices, and the color connecting two vertices labeled by t subsets is the size of the difference of these two. Okay? So you notice that for color number 1, we get the Johnson graph. So the Johnson graph is one of the constituents. In fact, this is the metric scheme corresponding to that graph. So the colors correspond to the distance in the Johnson graph. And so they have the same automorphism group. Okay? So if I look, for instance, at the Johnson scheme with parameters 5 and 2, then one of the constituents is going to be the Petersen graph. These graphs have a lot of symmetry. Their automorphism group is isomorphic to the symmetry group of degree k, and so they have exponentially n to the 1 over t automorphisms. And of course, the case t equal 2 is that's been bottleneck for the longest time. Okay, so once again, let's go back to primitive coherent configurations. So that means they are homogeneous. Every vertex has the same color, and every off-diagonal constituent is connected. Now, there is one among these that doesn't confer an awful lot of information, and that's the clique. Okay, the clique is a configuration of rank 2. It has only two colors. One is the diagonal, and one is off-diagonal. Everything, that's it. So we shall be interested in primitive coherent configurations of rank at least 3. So those that are not this trivial case, and they already have a rich structure. So this I call uni-primitive coherent configurations, or UPCCs. And so as a first example that something is already happening there, I proved in 80 around then that a uni-primitive coherent configuration has no more than exponential in square root of n automorphisms. Apart from from a log factor in the exponent, this bound is tight, as shown by the Johnson scheme with parameter t equal 2, and also by the Hamming scheme. What is the Hamming scheme with parameter 2? It has k-squared vertices arranged in a square, and then you connect vertices that are vertically or horizontally in the same line. You connect them with one color and everything else with another color, and diagonal is the third color. Okay? So these have essentially k factorial, or in this case k factorial squared automorphisms, so that's exponential in square root of n. So you can't improve this. Well, of course, there is no such result that you couldn't improve. Well, you can improve it with these exceptions if there are no other exceptions, right? So this is what we know, and then the challenge is to reduce this bound. Of course, you can't reduce it because it's tight, but reduce it with known exceptions. And that challenge was taken up by my student John Wilmes and Shaorui Sun, who is sitting right here. Where is Shaorui? Yeah, right there. Yeah. And they managed to push it down to n to the 1/3. The intellectual hurdles here are enormous. I mean, first of all, the fact that there are exceptions. It is one thing to prove something about all structures in a natural class of objects, and there is an entirely different thing to prove something about all but two classes. Okay? So one of the things they had to somehow do is separate, put a wide moat between these two and everything else. So they developed a structure theory, a combinatorial structure theory for UPCCs. There was none before, not even anywhere close. The only structure zero that remotely resembles what they got was known for strongly regular graphs. And in particular, in a certain range of parameters, they found an interesting clique geometry, and that, among other things, separates the exceptions, but it also has other roles. Okay, so I consider this the deepest result in the combinatorial theory of coherent configurations. Okay, so now a quick crash course on coherent configurations. Okay, so okay, I said that we are coloring the pairs, but from the color of the colors of the diagonal, we infer a coloring of the vertices. And so the vertices are going to be divided into vertex color classes. And so when I talk about color classes, I'm always going to be referring to the vertex color classes. The edge colors will be the constituents. Okay, now first thing to know is, these are easy exercises, that the color of an edge is aware of the color of its head and its tail. A corollary of that is that if I take any constituent, like the ice color constituent, then that is between either in a single color vertex color class or between two. So there are two types of constituents. There are homogeneous constituents, so that all their vertices belong to the same vertex color, or bipartite, so there are two, and all the edges of this particular color go between the two vertex color classes. So it is easy to show that a homogeneous constituent is a biregular digraph, and a bipartite constituent is a semi-regular bipartite graph. Okay, now here is some notation. If I have a relation and I plug into the relation a vertex, then that refers to the set of out neighbors of this. So the set of those vertices to which this x is connected by this relation. Okay, now strong components of a digraph are equivalence classes of mutually accessible vertices. Weak components is the same thing, except we ignore orientation. And then the fact that I already mentioned is that weak components of a homogeneous constituents are its strong components. Now, another fact that is maybe not quite as trivial is, but that's a nice exercise, that the weak components of the constituents have equal order. They have equal number of vertices. They are not necessarily isomorph. So for instance, here, let's look at the color, say, blue. Then these are the components of the color blue. They happen to be isomorphic because the examples I'm drawing are small, but if I could draw something with 16, then I could already draw two different ones, so that it would illustrate that they have the same number of vertices, that they're not necessarily the same. Another exercise is that they also have the same diameter, for instance. So all of them. And a lot of other graph theoretic parameters are going to be the same, but they are not necessarily isomorphic. Okay, so now let's look at induced subconfigurations. So first of all, a directed graph is just a pair where the second member of the pair is the set of edges, which I view as simply a subset of V cross V. So I allow self loops here. And a pair VC is a coherent configuration where V is the set of vertices and C is just the coloring. So C is a function defined on V cross V. Okay, now what's an induced subgraph of a digraph? I mean a sub-digraph, but that sounds a little bit cumbersome, so I'm going to call it a subgraph, but the subgraph of a digraph is a digraph. Nonetheless, and so this is the definition. And an induced subconfiguration is simply that take that subset on which we induce and restrict the coloring to the pairs in that subset naturally. Now, if I have a bipartite graph, then I denote it by, there is my bipartite graphs have a first subset and a second, so they are not interchangeable. And the set of edges will be oriented from the first to the second, okay? And then an induced bipartite subgraph is going to be a bipartite graph. So I take a directed graph. That doesn't have to be bipartite. But then I pick two disjoint sets, subsets of it, and then I just look at what happens between them. That's the induced bipartite subgraph, and that's the notation that I'm going to use a lot. So please try to remember this. If X is a digraph, A and B are two subsets that are disjoint, then this is the bipartite subgraph that is induced between these two. Okay? And then similarly, bipartite subconfiguration is defined analogously. So if I have a configuration and two disjoint subsets, then I restrict the coloring to the Cartesian product of those two subsets. That's going to be a subconfiguration. Okay? And an easy fact is that if I take a subset of the vertex set of a coherent configuration, which is a union of color classes, then the induced substructure is also a coherent configuration. CC will be coherent configuration. Okay, now here is an exercise. That's already now here. I am beginning to talk substance here. Okay, so let's look at a coherent configuration and two color classes, V1 and V2, and let's pick a vertex somewhere, anywhere. And now let's look at three colors I, J, and K. And now what I am looking at is I am going to look at the set U of, say, blue, I is blue, blue neighbors of X, and the set of red neighbors of X. Now you know that all blue neighbors of X go to the same color class, vertex color class, and all red neighbors go to the same vertex color class. Okay? So I look at this set, and now I pick a third color, let's call it purple, and I look at the restriction, I look at the induced bipartite subgraph in purple between these two sets, U and W. Okay? Then my claim is that this is semi-regular. Okay? This follows in one line. This follows in one line from the intersection numbers, but it is something nevertheless that we shall find very useful. Okay, so this is the graph that remains there. There are lots of other purple edges here between these two parts. In fact, okay, so between V1 and V2, purple has to be semi-regular. But I am only restricting it to the neighborhoods in red and in blue of this vertex X. And between that, that's also semi-regular. Okay. And now here comes what I call a theorem. The theorem is this. Let's look at our coherent configuration that is not shown here, but let me call, that's called X. And let X2 be the induced subconfiguration on this color class, V2. And let's assume some inequalities here. We have the same, so now X, first of all, my vertex X is going to reside inside this color class. In the previous picture, X was anywhere, either in or out of these color classes, but now it is in here. And I look at the red neighbors of X, that's W in this color class, and I look at the blue neighbors of X, and that's U, okay? And now what I am doing is, I am going to look at just the red edges also between these two. So these have the same color. Now let me just erase that for a moment, and let's see what are the conditions. The conditions are that this W is large but not everything in V1. So the condition is that it is greater than half of V1 but strictly less than all of V1. So that's an assumption. And the other assumption is that that's the interesting assumption, that the blue graph, of which I only shown a few edges, there are a lot more edges inside V2. Okay? So that must be connected. Basically what I am assuming is that the X2 restricted to this is uniprimitive coherent configuration, but for the purposes of this theorem, I am only going to use the fact that the blue graph is connected. Now, if it is a UPCC, it's a uniprimitive coherent configuration, then every off-diagonal color on V2 is going to be connected. And that's actually the way how I'm going to guarantee that the blue is, because I will not have a blue separately. I will just know that this is a uniprimitive coherent configuration. Okay? All right. So the claim is that under these assumptions, so these inequalities are being assumed and the blue graph is connected. These are the two things that are assumed. Under these conditions, the bipartite graph that comes here, this bipartite graph, so also in red, in the same color, this is, we already know that it is semi-regular, And my claim is that it is non-trivial. Okay? So trivial would be either no edge or all edges between these two parts. So the empty or the complete bipartite graph. And those are the things that we have to keep avoiding. So this is going to be, in recursion, this is going to be the loop invariant that we are dealing with, a non-trivial semi-regular bipartite graph. Okay? All right. So that's the statement. And I wrote here, this is the fix. Okay, so this result is at the heart. You may have heard that on the 1st of January, I got a really bad news from Harald Helfgott. There was a gap in my proof, and then a few days later, I found this theorem that fixed it. Okay, so basically the proof of this is 1 page, and the idea of it was already there in the paper. So in hindsight, this was not such a big gap, but in the first few days it looked catastrophic. All right, so so let's look at what we need to prove. We have to prove that this is not empty, and that it is not complete. Now the not empty part is going to follow from the assumption that this is greater than half. So W, the number of red neighbors of X, is greater than half of V1. Okay? But if the number of red neighbors of X is greater than half, then of course the number of red neighbors for this vertex U is also greater than half, because this is the red graph is semi-regular, so all vertices in V2 have the same degree. So therefore, these two halves overlap, so they have a common neighbor. But that common neighbor then defines an edge in this bipartite graph. So this bipartite graph is not empty because of the lower bound on W. Now we can drop the lower bound on W to prove that it is not complete. That's what we need to show. And so for that, there will be a lemma, okay? Twin awareness lemma. So if I have two vertex color classes, so this would be A and this would be B, in a coherent configuration, and I have a bipartite graph that goes between the two of them, that's one of the constituents. Then if I look at a pair of vertices, say in the upper color class, then the color of the edge connecting them, it can be directed. I didn't draw an arrow there. It can be directed or undirected. But that color knows, it is aware whether or not these two vertices are twins. In a bipartite graph, to be twins means that they have exactly same neighbors. Okay, so if you look at these two vertices, then you see they are the heavy edges. They have the exact same neighbors. This, and this. These are the common neighbors. These are exactly the neighbors of both of them. And so if I have another red edge, then this lemma asserts that those two vertices are also going to be twins. Okay, again, it's not difficult to show, but very useful. So this is the twin awareness lemma. Okay, and now let's go back to the theorem. So again, if X2 is a UPCC, we take a vertex from the lower part. And now I am only assuming that this upper neighborhood of X is just not everything. Then my claim is that that bipartite graph in red between them is not everything. Okay, suppose, so it's proof by contradiction. Suppose it is complete. Suppose this is complete. If it is complete, that means that in particular, if I pick a vertex U down here, then it is adjacent in red to everything in W. But we know that they have X and U have the exact same number of red neighbors. So that means that this is the entire red neighborhood of U. So that means U and X have the exact same set of red neighbors. So in the red graph, they are twins. Oh, but they are connected by a blue edge. But the blue edge is reached everywhere. And so the transitive closure of blue is everything. So therefore, all of them down here will be twins. That means that the red neighborhood of every vertex down here is exactly the same set W. Oh, but that's impossible because then the red degree of these and these are not the same. I mean, this is supposed to be a semi-regular bipartite graph, and here the degree is 0, here the degree is full. So that doesn't work. So all we used is that this set here extra is not empty. Okay. All right. So how are we doing? Okay. Yes. Yes. Okay. All right. So, so let's go back to Splitter-Johnson. And now, okay. So this was a lemma about coherent configurations, and I'm going to show how to use that to settle one of the cases of Splitter-Johnson. Okay, so I am just putting up Splitter-Johnson once again. So good coloring means there is no dominant color, where dominant means at least 90%, but it would be enough if I say 51%. And the good equipartition is, I am talking about a good equipartition if it is the case that there is a dominant color and that color is being split up into a non-trivially into equal parts. Okay, so this is then Splitter-Johnson. And now, okay, so what was the input here? The input was a graph with symmetry defect at least 0.1. So no greater than 90% could be covered by a symmetric group action. Okay? Now here is a variation on this. There will be several variations of this, which are Splitter-Johnson for certain type of structures. Splitter-Johnson for uniprimitive coherent configurations. Okay? So in this case, I don't need to assume anything about the symmetry defect of my input uniprimitive coherent configurations because every color class there is a regular graph there or a biregular digraph, so it has symmetry defect at least 1/2. So I am completely safe here, and then I again have the same alternatives. All right. Now,
is there a good point to take a break at some point?
Yeah.
Oh, a break.
Yeah. So that's what I was trying to say, maybe.
Oh, okay. Actually, I don't know. Yeah, sure. Let's take a break. But how many breaks are we taking? I guess. Let me just see.
It used to be half an hour, and now it's probably
One? No, but what is the actual schedule? Let me see. What was that?
10 minutes over time.
Oh, I see. Okay. Oh, we are taking a half an hour break, it says. Okay, all right.
Let's take 25 minutes.
Okay, all right. So sure. Let's take a break then. Okay, this is a good point to take a break. Yes, thank you.
Any questions now, or maybe after the second part?
Well, I mean, anytime. Questions? Yeah, I mean, in the middle of the sentence.
25 minutes. We resume 5 past 11.